Okay, related rates example 2 coming your way. This example a little more difficult. There's some subtleties. There's some careful reading that has to take place if you're to get a problem like this correct. And you can really find yourself in a circle chasing your tail if you are not a careful reader. Remember, you're not reading a novel here. These word problems, every little sentence and piece of information counts. So you have to take into account each piece carefully in order to land this plane. Let's take a look at example 2. So this is example 2. Remember this scene from Star Wars? Back in the old days, and they're in this trash compactor and the walls are moving in at a specific rate. You probably didn't catch that when you were watching the movie. And this has got, this trash compactor's got a nasty liquid in it. And as the walls move in, the liquid is rising, of course. And we'll see if our heroes can save themselves. But maybe you are familiar with this scene in Star Wars. If you're not, that's all right. So anyways, here's a little diagram of this trash compactor and the liquid that's inside. And we're going to label these because the word problem labels the walls as a side wall and an end wall. And the two end walls are moving toward each other. That's what those arrows represent. And you can see then that the liquid is rising as the end walls are moving together. The liquid inside is not changing with regard to its volume, but the height of the liquid is indeed changing, and that's what we're going to try to find the rate at which the height is changing. So here's the word problem here. It says, Luke, Leia, and Han are trapped inside a trash compactor on the Death Star. The end walls are moving together at negative 0.2 meters per second. The volume of the liquid inside the compactor is a constant 20 cubic meters, and the end walls are 4 meters long. Now, the end walls are not changing their length during this scenario either. The sidewall exposure will change, but the end walls are staying a constant 4 meters long. That's important. Then it continues, at the moment the sidewall has shrunk to 3 meters of exposure, find the rate at which the depth of the liquid is increasing. So the big picture here, the end walls are moving toward each other. The depth of the water is getting squeezed, so the depth is increasing during this scenario. Let's figure out the rate at which the water height is increasing the moment the sidewall has shrunk to 3 meters of exposure. All right, so again, we're using dreads. And we've got a nice diagram already. Pretty impressive. And now we're going to record the related rates. Well, in the problem, it says that the end walls are moving together at negative 0.2 meters per second. But the end walls, you guys, aren't changing. The end wall's length is not changing, not at all. It's the side walls, or the sidewall exposure, that is decreasing at 0.2 meters per second. So this is one of those be a careful reader scenarios that you got to watch out for. This is correctly labeled. The derivative of the sidewall with respect to time is decreasing at negative 0.2 meters per second. Okay, so that's a serious be careful caution. In the end, we were told that the volume of the liquid inside the trash compactor is 20 cubic meters, and that value is not changing. But the other related rate that will be changing is the height of this water. As the end walls move toward each other, the height is increasing. That's what we need to figure out when the dust clears. So now we have recorded our related rates. We got to come up with an equation. Well, this is a simple equation. That's a Kraken box. And we know we got to talk about the volume of the box. Well, the volume of a box is just length times width times height. there we've labeled in the picture the height of the water, the depth of the water. And remember, the end wall is 4 meters, and that distance is not changing. So these two cats here are not changing throughout the entire story problem. This is going to allow us to insert those values immediately when we write down the equation. We don't have to take the derivative first and then substitute those values in. If they are constant and unchanging throughout the scenario, we can insert these values into the equation at the very beginning. So again, we're at this step where we need to come up with an equation. Well, I know the volume of boxes, length times width times height. I'm going to use some user-friendly variables here, see if you guys buy this. S times E times H, you know what those letters stand for? The volume equals the side wall length times the end wall length times the height of the water, the liquid, okay? And now I'm going to put in 20, since that is an unchanging value. I'm going to put a 20 in for volume. The side wall length is indeed changing. The end wall is a constant unchanging value of 4. And the height of the water will be, height of the liquid will be changing. So right now, our equation that we're going to use is 20 equals S times 4 times H. I'm going to go ahead and divide both sides by 4 and have this equation 5 equals S times H. And we have completed finding an equation for this problem. It's now time to take the derivative. As we catch up here, we're going to take the derivative of that equation, and we're going to do so implicitly. So we have this simple equation 5 equals S times H. If I'm going to take the derivative of that S times H, I got to use the product rule. So the S, I'm going to make a U, and the H, I'm going to label as V, and realize that the product rule tells me I got to go U prime V plus UV prime. Remind your neighbor, you got to do so implicitly. So you can really fall off the boat here if you forget to do this implicitly, or if you forget to do the product rule. I've seen it before, okay? So you got to be a careful cat here. So now let's see if we can do this. I start with a 0. How'd you get 0? Well, when you take the derivative of 5, the constant 5, you get 0. Equals, let's see, when you take the derivative of u, you get 1 times ds dt. This is implicit differentiation, which you learned a couple days ago. Times leave v alone, so that's why we have the h there. This is part of the product rule. You leave the term v alone. So I have 1 ds dt times h plus leave u alone, which is the s, and then take the derivative implicitly of h, which you get 1 times dh dt. Here is the derivative equation. Congratulations, you found the derivative. Now, we're going to substitute and solve. Well, do we have a ds dt value to put in? Yeah, it's in that blue writing above. ds dt is equal to negative 0.2. We still have an h, so let's get to work on this h. We can find out what this h equals. At this moment in time, remember, we're told the volume is always 20. Further, we're told the side wall is always 3. No. The side wall is 3. The end wall, the side wall has decreased to an exposure of 3, while the end wall is a constant 4, sorry. All right, and then times h. We've already taken the derivative here, so now we're putting in these values and solving for h. Well, h is going to be equal to 5/3. Only now I'm able to put in that 5/3, you see. I have to take the derivative first because the h value is changing. So any value that is changing, you have to wait to put that in until you are to the substitute and solve portion of the problem. So I now know that h is equal to 5/3. I'm just writing right below the yellow sentence there. The ds dt equals negative 0.2. The h value is 5/3. plus S. What is S? A sidewall. Yeah, the sidewall they said was 3 times dH dt. You can see what happened with the computation with the first term. Negative 0.2 is negative 1/5. Think of that, negative 0.2 is negative 1/5. So you have a 5 on top and negative 1/5, a 5 on the bottom. That's where I'm getting that negative 1/3. Negative 1/3 plus no change. Now I got to solve this for dH dt. What I'm going to do is add 1/3 to both sides of the equal sign and get 1/3 equals 3 times dH dt. Then I'm going to multiply both sides of the equal sign by 1/3. Hopefully you can see here algebraically you get dH dt equals 1/9 meters per second. All right, so that should say to you, what did I just figure out as I did that problem? Yeah, as those walls are moving toward each other, the liquid in the trash compactor is increasing at a rate of 1/9 meters per second. It's not always increasing at that rate. Shoot, when this thing's big wide room and the end walls start coming together, that height is not increasing. The depth of the water is not increasing all that fast. But toward the end of the scenario, when it's crunch time, you can picture the height of the water is increasing at a much faster rate. So at this point, the rate at which the depth of the water is increasing is 1/9 meter per second. So you always need to write these, you guys, and interpret these correctly. ATM, at the moment. At the moment, the sidewall has shrunk to 3 meters. The height of the liquid is increasing at a rate of 1/9 meters per second. That's how you end the story here, and that's a related rate problem that's a little more difficult. Hopefully with some practice, you can master related rates problems. There's 2 types of calculus students. Some calculus students, you ask them at the end of the school year, hey, what's the most difficult concept that we've had? Ugh, related rates problems. I hate related rates problems. Other calculus students, you ask them, what's the easiest concept in calculus that you've had? They say, related rates. Because I love the sequential steps. Give me DREDS and I can always figure these out. So depends who you are here, but I'm going to suggest if you spend the time necessary to master this stuff, you can do it. You can do it for sure. So give it a whirl and your best shot. Ask questions in class and giddy up. Over and out.